Okay, we are live on the stream, so whoever is going to be doing the introduction can go ahead anytime.
Welcome, everybody. It's my pleasure today to welcome Yair Cohen to our Colloquium series. Yair did his PhD at the Hebrew University of Jerusalem in 2016. Working on the linear instability of synoptic scale eddies in a two-layer shallow water model. More recently, he's gotten interested in moist processes and convection. And he did some studying of entrainment processes and has been developing a convective parameterization for for the CliMA project. So he's worked in particular on convection and turbulence and the Monin-Albikoff surface layer. And he's done some of the convective parameterization development through looking at large eddy simulations and diagnosing those. So some connection to smaller scale convective models as well. And he's going to tell us about some of this work today. Thanks for being here.
Thank you for the introduction, and thank you for the invitation. Still see people coming in. Maybe I'll give it a minute or we can start. Okay, thank you, everybody. So today I'll talk about, the title says, convective parameterization in general, but more specifically, combining physics and machine learning in a turbulence-convection parameterization. And one in mind to go to the CliMA climate model. I would give a little bit of overview of CliMA in one slide just to let you know what's the context of it and what is the mission or goals of the project and how the convective parameterization fits in them or develop towards them. This work has many collaborators. You see the list here. I'm not sure it's even everybody. So just to say, this is not just my work. It's what we do as a team that developed convective parameterization. I was a postdoc of Tapir, and now I'm a research scientist in the CliMA project, and I'm leading the development and implementation of this convection parameterization model in the climate model. And many people here are related to different parts of work. And also some of it is in progress, and I will have a little indication that it is in progress. So some of it is already published and some is still being processed and refined. And this is Alma, and she was born 5 weeks ago. And because the talk is from home, you might hear her giving vocal guest appearances in the background. I apologize in advance. We tried to time their feeding so that it wouldn't be, but that's how it is. And I guess it's not the worst thing that can happen on Zoom these days. So let's start. So just a little bit about CliMA. CliMA is an acronym like anything for Climate Modeling Alliance. So the idea is that it's a climate model developed by universities, which is unique. Typically they're developed by modeling centers and government labs. And the model is completely new. It's developed completely new in a new programming language, Julia, that has the appealing benefits of today's modern programming languages that were used at the time to justify Fortran. It's user-friendly, but runs in parallel and work fast and can do many things with it. I wouldn't go too much in the coding part. The premise of the climate model is to have what we call an Earth system model, a model for all climate system, land, ocean, atmosphere, ice, biosphere, etc., as listed here. And the idea is that the model would have a data assimilation and certainty quantification machine learning layer that interface from the model to external sources of data. These could be observations from satellite or high resolution simulations in the ocean or atmosphere or ice processes, or even in situ measurements. And every time that new data comes, this Bayesian approach model would have to update whatever parameters or parameterizations or closures based on the new data to improve the model while it's running on the fly, not in hindsight, not to rerun the model with the new data. So that's basically the overarching. And as I said, I'm involved with the cloud parameterization and turbulence part. And I'll give a little outline and dive into the talk. So first I would give a motivation for convective parameterization and why we're doing what we're doing. I would describe the physics-based EDMF parameterization. EDMF stands for Eddy Diffusivity mass flux. So we combine the Eddy Diffusivity approach of turbulence and the mass flux approach of convection into a unified model. It's an approach that's been around for about 2 decades, and I think is gaining momentum in the last couple of years in the convective parameterization community. After describing the model, which will be uniform across all implementations here, I will describe the physical-based closures. These are the closures that don't involve any data-driven methods. They come from physical ansatz or arguments and scaling laws and stuff we understand about or think we understand about turbulence and convection. I would show the results of only the physical-based closures, and these are results already published. And then I would go into the calibration and training of gradient-free approach and the machine learning part of the closures, which is more in progress. I will try to make a few breaks for questions, but if you have a question, I'm fine with whatever the practice is here. Typically ask me in the middle or wait for the end, it's up to you. So motivation, I think this is the best example of motivation. This figure from Brian et al. From 2019 shows the bias in low cloud fraction between one Calypso satellite product and one climate model, CNRM. Let's see, I'm assuming you can now see my cursor better, so it's nicer. And you can easily find biases here up to 50%, and the map is saturated. Technically, you actually have biases here much higher. Like you could have found 70% bias in the stratocumulus-topped here in the west of continents. The most obvious biases in low clouds are in the pole and in the west of continents. In the pole, it's too much mixing over polar boundary layers that are stable, that carries moisture too high up and quickly condense directly into ice clouds and create clouds that are not there in observations. And in stratocumulus-topped, it's almost the reverse. You don't mix well enough, or you mix too much and you break the stratocumulus clouds and you have a negative bias. Now, this bias is very important for the climate as a question, and this figure from Schneider et al. Is correlating a scatter plot of low cloud fraction of reflectance change. So that's how the reflectance of low cloud changes when you change the climate in a climate warming scenario, and the equilibrium climate sensitivity. And each dot here is a different climate model. So we have 29 climate models here, and they're color coded by the most sensitive and the least sensitive. So the most sensitive climate model is the reddest, 29, and number 1 is the least sensitive. And you can see that there is a fairly good correlation that models in which when you increase the CO2 and the globe warms, you get more cloud reflectance, meaning clouds are radiating back more, are those that are least sensitive. And those in which when you warm the planet, you actually get less cloud reflectance, are those that are most sensitive to global warming. This ECS, equilibrium climate sensitivity, means that you wait until the system equilibrated and the ocean flipped and such to see the response, basically. And the problem is a problem of scale. So, the planet is a scale of 1,000 kilometers, thousands of kilometers, and cloud is a scale of 1 to 10 kilometers. And that's a big argument now, it's cloud resolving or not, but around 1 to 10 kilometers. But the processes that actually control the development of a cloud are happening at the sub-100 meter scale. And some people would say even centimeter if you go to microphysics and such. And obviously, we do not have the computational power to simulate all the scales of motion in the climate for 100-year simulation with an ensemble of simulations to, eliminate uncertainties and such. And this figure here from Schneider also shows the years of the x-axis and the horizontal resolution, 1/kilometer, so increasing resolution upward over years. And each of the blue dot is basically showing the doubling of the computational flops or computational ability increasing every year following what's called the Moore's law, which is basically a prediction of our ability to miniaturize the components in transistors, that we would double our computation every 1.2 years. And each of the orange markers shows a different type of climate model. So AGCM would would stand for atmospheric GCM only. AO GCM would be atmosphere ocean. ESM is air system model, what I described before, the full complexity of ice, biosphere, etc. And we see two things here. First, we see we don't really follow the curve of computation because as the resolution or the computation increased, so did the complexity of the models. And you could argue if it's for good or bad, but that's the reality. It's kind of like every year our laptops are stronger, but Microsoft Word becomes slower because the rate of features added to Microsoft Word overwhelms the increase in computation. And the other thing you could see that if you were to extrapolate to the future, and we can't really, because Moore's law is about to end, that now the scaling of components in microchips is about to end. And so unless some quantum leap in computing would come, we're expecting some difficulties and continue this trend into the future. But even if you would, and you ask yourself, what is a LES on the globe, it would probably be north of 2060. And by then, most models predict some drastic changes in the climate that need to be addressed. So for decision makers to really get better estimates of how bad is the situation and what measures to take, we're going to need to give them answer before we will have a global LES. One thing that is happening that is more optimistic, that with years, the domain in which you can run an LES simulation has increased in size. So that's going downward in this reverse axis. But the point is that now in 2020 or a bit earlier, but we're somewhere in a place where we can run an LES on a single grid box of a climate model, even though we cannot run it on the entire globe. So we can really study clouds and turbulence in each grid box of a climate model. We can't do it all over the globe. And we're trying to leverage this ability now in developing the parameterizations. So here's a visualization of what it means. You have a global model with a dynamical core showing here on the left. And in each grid box, you might be able to run a LES, which you see in the video, with all these complicated motions of liquid water in this gray contour and the temperature or buoyancy at the surface in colors. And running one LES on one column of the globe is as expensive as running the dicore on its own resolution for the entire globe. Okay, so that's roughly the scale. So that running an LES on the entire globe would be very, very expensive, and it's out of our reach. The equations which we solve on the global, they have these angle brackets here for average. We solve some average quantity of any scalar that you like, temperature or whatnot. And these equations, obviously, because of the averaging, include these Reynolds averaging terms, which are in the blue square. And these are basically the missing terms that require closures or parameterization. So this is the goal of the parameterization. There is a bit more than that, because in the last term in the equation, the source, there is also radiation, and radiation is a cloud fraction. So the parameterization interacts with two terms in the equation, but to keep it simple, let's just imagine we're focusing on this term for now. And I think it'll make the discussion easier. So what do we do? What do? We assume that there is some kind of a distribution of upward and downward motion in this video, in this LES. And we assume two fractions of area of upward and downward motions, updraft in an environment, over the grid box of the GCM. And we write equations to represent a host of processes that we think that prevail within the upward, the updraft, and the environment, such as vertical velocities and microphysical rain sources and evaporation and snow, and entrainment and detrainment, and pressure effects and radiation, and turbulent mixing, which prevails more in the environment, and so forth. And we write down the equation, and then we're ended with these terms in colors, such as entrainment, which require closure. And at that point, we kind of hit a wall. We start diagnosing LES, we start coming up with physical arguments or length scales. And that's the point where we at least argue we can plug in machine learning if you have the right architecture for it. So just to say, most climate models today have kind of almost a cartoonish stack approach of parameterization. It's not fully true, but it's just a visualization to help us differentiate. So you might have a boundary layer parameterization, and above it a stratocumulus, and a shallow convection, and a deep convection parameterization, and some trigger function to say when do you start stratocumulus or shallow convection, and so forth. And these functions make the calibration of this model really hard because the switches are non-linear. So the map in parameter space become very difficult. The unified approach that is kind of embedded in the EDMF is to say, let's divide the grid box in the horizontal into updrafting environment, but keep it vertically uniform. And now the challenge is the interaction between the cloud and the environment. That's where all the details are buried. I mean, the idea is that such a parameterization, and I'll show you, could serve to simulate everything seamlessly and continuously from boundary layers to deep convection. So in a way, it's a coarse-graining exercise. You can think of the AES domain in a highly resolved domain, and the parameterization is accrued with only 2 grid boxes that have kind of dynamic boundaries. And if you would label each grid box on the left as going up or down, you could attribute it to the updraft on the environment very crudely. And then you would like to have a model on the right, which is very cheap to run. It's 1 minute on a laptop, in opposed to a few hours on a multiple cores, that's plugged inside the GCM in every point to give you a measure of the cloud function or the vertical fluxes. I would introduce some terminology. So if we have a variable phi, the mean over the entire grid box domain would be the angle bracket, and the perturbation would be an asterisk. And the same variable in the updraft, the mean would be a bar with some u for an updraft, and the perturbation would be a prime. And the interaction between this mean and perturbation is the crux of the matter. So the mean in the domain would be the area weighted mean. A here is the area fraction of the updraft. So the area weighted mean of the updraft property and the environment property. And the covariance, in that case with W, because we remember the GCM equation, would be area weighted combination of covariance in the updraft and environment plus a third term, which is very important and comes up of applying this Reynolds averaging. And that third term is what we call the mass flux term. And so if you think of the distribution we had before, the mean of the updraft is the mean of that distribution, the mean of the environment is the mean of that distribution. The covariance here, if phi was W, so it's more one-dimensional, the covariance here is the width or the square width of this distribution. Covariance in the environment is the square width of this one. And this term relates to the square of the distance between the 2 means. And so in a way, you could see we want to rebuild this distribution. We need to solve equations for all of these variables. And that would be our parameterization model. Just to remind you, or one more thing, the EDMF assumes, the parameterization right now assumes that the updraft is a delta function, so it has no variance. And this is not correct, but it's for mathematical simplicity. We can see how far we can get with that. We can always add more updrafts to get some kind of a measure of variability by having multiple updrafts. It's not clear what's the trade-off. Is better to just include the variance of the updraft or to have 10 updrafts and it's left to explore. So just to remind you, this is the climate model equation, and this is the term we're looking for. And that term is related, using the composition of updraft and environment, it's related to properties in the updraft and environment, to mean and variances. And if we will write down equations for all of these, we can come up with a prediction for this term to fit in the GCM. So that's an introduction to the parameterization problem in general. These 2 slides are equation heavy. This is the next one. I'll try to walk you through it without getting lost, okay? These are the updraft equations in the model. So you have the time dependency on the left, except for this one, but it's okay. I neglected the horizontal divergence term because we're still in a single column setting where horizontal divergence is 0, but otherwise it will be included here. And what's important is these terms that are color coded. So all of these terms require closures. All of these are physical processes that are part of our exercise of coarse graining the LES equations into this updraft and environment. And we don't really have a good counterpart for them in LES. We can try to diagnose them, and we have to come up with creative physical intuition, ansatz, scaling analysis, or machine learning in order to represent them. So in blue, we have what we call entrainment and detrainment. There is the dynamic and the turbulent component of entrainment. In red here, the source, so phi could be a thermodynamic quantity, and the source would be microphysical sources such as rain formation, evaporation, etc. And in green would be the non-hydrostatic pressure effects that typically act as a pressure drag to slow down the motion of rising bubbles. So these are the updraft equations, but we also need to solve for covariance, at least in the environment. It's achieved, the equation is achieved by taking the following operation on your existing equation, assuming that, product of two variables is one variable and writing this combination. The equation is very complicated. I'm going to show it and I'm going to cover it because it's almost gross. So I want to give you like a minute to breathe. So I'm covering it. I'm just giving labels here for the different terms. And the important part here is that it also introduces a turbulent flux, which requires some eddy diffusivity closure. And that eddy diffusivity we take to be proportional to mixing lengths and the square root of TKE, turbulence kinetic energy, so that we add to the list of closures that we need upon the one in the previous slide, also this mixing lengths. And I will show the terms, but they're really nasty. What we have here is basically counterparts of terms that you might know better. So the vertical flux has almost a horizontal flux, which is the dynamic entrainment part, and the turbulent part would have a turbulent flux, which is like a turbulent entrainment, and the shear production from the gradient will have a counterpart. It's not really crucial. Oh, sorry, it's not really crucial. And maybe I will give it a pause here. I would see if there is any questions. And in the meanwhile, just say, up until now, I gave you motivation for why to parameterize, because we are not going to have the computation to globally simulate clouds in a reasonable climate simulation for long term. And also, like, just to recap, we got a model that is in a way coming from the LES equations, but just coarse-grain them into something simpler that would be mathematically complicated, but computationally cheap, and requires a lot of unknown processes. And this would be the crux of the matter, would be these physical closures. If anybody has a question, please go ahead. If not, I will move on. Let me know. Okay, we'll keep them to the end. So the first one would be entrainment and detrainment. So here is an updraft, quote unquote. It's actually dye falling in water, but you wouldn't know I flipped it upside down. And what you see here, if the color represents, let's say, the momentum or the concentration of tracer, is that as the updraft goes up, it mixes with the environment and the color fades. And entrainment basically is a process of decision. If you mix some air from this updraft with its surrounding environment, is the mixture also going up, meaning joining the updraft, so it entrains, or is the mixture buoyancy-wise, it's zero or negative and it stops or going down, and then it would be part of your environment, and it would be detraining. And so that's the entrainment detrainment. Now, in this dry scenario with no phase changes, you mostly entrain because the updraft is much more buoyant than the environment. So you take, 5 and -1 and 5 and -2 and 5 and -1/2. You always get buoyant, less buoyant, but buoyant mixture. And so you just entrain, and the updraft is almost linearly or exponentially growing with height, depending how intense it is. And that's kind of simple. The interesting part comes when you have moisture. So in moist conditions, if you have a buoyant parcel with water drops in it, with liquid water, and you mix it with a dry parcel of zero buoyancy, the evaporation of the drops would drop the buoyancy to be negative. So if you like, you can mix 1 and 0 and get -1/2, okay? And so that process of evaporating water drops creates what we see in clouds, where they detrain all across their vertical structure, not only at the top. The cartoon is not ideal here, but I just wanted to show that the area fraction is more or less constant. Whereas here, the mass flux is more or less constant. So these are kind of the differences. And so in modeling approach of these processes, we're going to do something you're not supposed to do and assume that we can break buoyancy into a dry and a moist component of the process. That should not be done because buoyancy mixing is nonlinear, but we will do it and we can see where it goes and what is the limitations of doing that. So let's look at entrainment, and it's kind of, we have a mixed layer here and we want to know maybe what is the scale of this mixed layer. And from arguments that the vertical velocity and the area fraction has to vanish together with some mathematical from the L'Hopital rule, you can actually come up with a length scale or inverse length scale for entrainment, detrainment that is highly cited in literature and seems to be very accepted by the community, which is the buoyancy of the velocity square. So this would be that length scale. And now what we're doing is we want to combine this buoyancy velocity scale with non-dimensional quantities for D for dry and M for moist processes. And we can do it, dry entrainment and moist entrainment, dry detrainment and moist detrainment is kind of a matrix, but really what happens is you have dry entrainment and moist only detrainment. So only the diagonal is really happening. if you have a descending downdraft in a moist environment, you might have kind of off-diagonal term, but typically it's really the diagonal that matters. And just to remind you, so this would be the moist process and the dry process, and we're doing something we shouldn't. We kind of like separate something that is nonlinear and cannot be done with some kind of Taylor expansion like that. And just to recap back, when we looked at our equations, what we really had wasn't epsilon and delta entrainment detrainment. We had rho A W epsilon and rho A being the area fraction W delta. So if you just multiply, you see that actually, and I think this is a subtle but important point, the important scale is actually B over W, but now it's a time scale, okay? And there's a reason, because if you take B over W squared, the sign of W doesn't matter anymore, but when you look at B over W, the sign of W and B is what kind of like the crux of the matter. So if you imagine an updraft and a descending area in the environment, and you say B over W is the relevant time scale, and it's a problematic time scale because there could be positive in both places, right? Because you're going up here and you're buoyant, you're going down here and you're negatively buoyant, so you're always positive. So B over W doesn't help you decide, like I said before, is this mixed parcel joining the updraft or going to the environment? And so what we did in our paper is we try to think of ideas coming from papers in the 80s of buoyancy mixing, but not really doing buoyancy mixing in that same sense, but does think about the mixture buoyancy. You think of mixing the buoyancy of the updraft in the environment and putting it here, and there need to be some assumption about what fraction of air comes from the updraft and what from the environment, and that would be a tunable parameter. And then you can kind of mix the two buoyancies and ask, is this buoyancy relative to the mean buoyancy? Is this positive or negative? And what is the velocity difference between the two domains? And this really allows us to partition between entrainment and detrainment more efficiently. So we turn that mu, this quantity, and you could say positive or negative mu would give you either each. Instead of a sign function, positive or negative, we just took something logistic that changed more smoothly as a general approach to keep our model in smooth behavior when we think future about calibrating it and stuff, that sharp jumps and functions are very bad. And I made some geometrical arguments that this mixing fraction high should be basically 1/4 if you think that, you know, an eddy that mixes the updraft with its surrounding shell has similar horizontal extent into the shell and into the updraft. This would be a planar view looking at the updraft from the top, kind of a cross section. Then, you know, the area would tell you that it's 1/4, but it's really is a tunable parameter that could be learned from data. So we have our dry function that was a bit of a long ride, but the moist part is a bit of a shorter ride. And the moist part is completely ad hoc. So I'm reminding you, we said, you know, you evaporate the water drops, you create negative buoyancy. And so it seems like the drier the environment, the more likely or fast you would evaporate drops, and you would have more of the pool of air out of the updraft than you would in a moist environment. And so we took just the difference in relative humidity with some power and an index power, this beta, which is now just 2. So this is squared square root, to be the moist component of the detrainment. And without too much explanation around it, I can remind you what our formulation. I can show you some encouraging results. So this is large eddy simulation only here of shallow convection over land, where shallow convection penetrates into a dry layer. It's in the Great Plains. And you could see that by the environment relative humidity dropping above 2.5 or 2.2 kilometers. In the solid line, let's look only at the orange now. Orange would be detrainment. The solid line is direct diagnosis of detrainment from LES with all its complexities of using tracers and identifying updrafts that I'm not diving into. And the dashed orange line is diagnosing the different terms in our closure and plotting them. So there's no parameterization here, it's just LES. And what you really see in both of them well is that once you enter the dry layer, the environment just pulls all the air out of the updraft. There is a massive detrainment. And we're arguing that this is capturing well the phenomena and good enough to work. And we will see when we judge the results. I would give a side note of in progress. We're working on adding stochastic components to our moist and dry processes. And so this is just a simple result of some vertical velocity in a shallow cloud simulation, our deterministic entrainment here on the left, and our stochastic entrainment on the right. And it looks much more like LES in that it has this ragged variability in time. This is time height slices of the vertical velocities in the updraft. You really reproduce the variability you could see in LES, which is really impressive. This is work by a PhD student named Hakon that is ongoing and probably would, work towards a publication throughout the year. So that's just a side note. I mentioned before the closure for pressure gradient or non-hydrostatic pressure. So it's really helpful for us to think first what the LES does, because we're coarse-graining the LES equations. The LES actually has a Poisson solver, basically says what would be the pressure so that the three-dimensional divergence of the velocity will be 0, or more correctly, the tendency of the divergence will be 0. You start with 0 divergence, you stay with 0 divergence throughout the simulation. And you can think we need to replace this process in a way by some kind of a model for the pressure gradient. Now in this video, you're seeing the pressure gradient acting on a bubble experiment in LES. And you can see the positive and negative effect of it. So this is a slowdown, the blue, and the red is speeding up. And here is a diagnosis from some shallow convection simulation of a single bubble. And you could see in a way the similar process of speed up and slow down acting on the thermal bubble. And so based on some normal mode decomposition that we did on the field in an idealized bubble, you can come up with 3 terms. One and 2 of them are very known. There's a virtual mass effect and a pressure drag. The third one is more new. It's a momentum convergence, and it's the only one that could be positive. You can explain these red parts here at the bottom. And these are our pressure, this is our pressure closure. And as you can see, these alphas are actually tunable parameters that could be adjusted accordingly by calibration from data. The last closure is the mixing lengths. And I think this part might look cumbersome, but after this, we'll look at more results and I think it'll be more fun. And with mixing lengths, honestly, I think this is the more complicated work we published. It's really, and I think that it's really important to delineate the basic physics behind the complex problem. So the mixing lengths in a way is, it's the mean free pass of air parcels before they dissolve their environment. It's an analogy that the Prandtl had to, Brownian motion or such. And you can ask yourself basically what limits mixing. An air parcel wants to move up or down, what limits the motion? And the 2 obvious one are the wall, of course, the distance from the ground. You can't move past the ground. So that's kind of limits the mixing lengths near the surface. And you can assume a stable layer, if this is potential temperature, would limit mixing as well, because it's almost like a wall. It's not rigid, but it's semi-rigid. But what happens in between? That's the key question, basically, for the mixing lengths. So we're going to combine these 2 mixing lengths with a third one for what happened in between and arrive at the general mixing lengths. What happened in between, what we think happens in between, is that you have balance between terms in the TKE equation that produces a mixing length. And so what limits the mixing is the amount of turbulent kinetic energy you have, not a wall because you're far away from either of them, but rather the amount of TKE. And what you see here over time is several tendencies in the TKE equation in a stable boundary layer simulation in LES. And you can really see they mirror image each other. It means that the tendency of TKE is a small residual between big players. These big players are the production from shear as air flows over the boundary layer, and the dissipation by cascade down to smaller scale, the buoyancy, production or destruction, and the transient terms such as advection, and maybe even not in this simulation, but if you have updrafts, the updrafts dump momentum to the environment and create decay and so forth. And so the assumption is, and look at the text even, not the equations if you want. If you just assume that these terms balance each other in the TKE equation, you can just write a balance between production and dissipation of TKE. And all of these terms are proportional to the mixing length. So one can isolate the mixing lengths from them to arrive at a formula. I didn't even write it here, it's quite big, but I can show you how it performs in a stable boundary layer. So if you remember the 3 lengths that we had, the distance to the wall, the buoyancy, and the TKE, here are they color-coded over time in a stable boundary layer simulation over the pole. And you could see that indeed in the lowest part, the distance from the wall is governing mixing, and at the top part, the distance to the stable layer governs mixing, but somewhere in the middle, it's the balance of TKE that actually produces the right amount of mixing. Okay, now I'll do a second pause in my talk because I believe it was already quite a lot, I'm sorry. And if there's any other question, you're welcome to ask. And if not, we'll proceed. Anything? Okay, I will do a short summary. So I motivated parameterization of convection as a way to simulate subscale processes in climate models in the resolution that's available for us today. And I showed you our parameterization coming from coarse-graining, what we look at as truths, the LES simulation, which gives us very good cloud and turbulence simulations, into a smaller, cheaper model we can run on the laptop in a minute. And then I've went through the equations and through the different closures that we propose for them. And these things could be disentangled. Somebody might take our model but come up with different closures, or somebody might take our closures and apply in a different model. But for us, they're a unified piece. So now let's look at, yes, sorry. Oh, no. Now let's look at simulations. So here is our bias map from before of low clouds, just to remind us where things are. I would start with the polar boundary layer. So this is a 400-meter deep simulation of a boundary layer over ice in the pole with a stable stratification. The challenge here is that you have wind shear producing mixing at the surface, but that mixing cannot penetrate too high. If it does, it lifts moisture to a level where it freezes literally, and you get icy clouds. And you can see that climate models have a positive bias. They produce too much icy clouds at the pole, meaning they mix too much. And what we see in solid line here is large eddy simulation for the UV velocity components, and shading is a range of LES in literature. And all the dashed lines is our parameterization for different resolutions, ranging from, I believe it's 5 to 75. Okay, so even resolutions reasonable for a climate model such as 75 are still giving reasonable behavior in that sense. The second would be its cousin. It would be a convective boundary layer, where the boundary layer grows because convection keeps growing and penetrating it into the stable layer and pushing it up over day. It's kind of a textbook case of convection. And here I'm showing the theta and QT profiles. There are various resolutions here, but it's hard to even see the difference between them. So we just look at the gray as LES and the color as our single column EDMF parameterization. And the next one would be a boundary layer clouds or stratocumulus clouds, where I'm showing the liquid water. So it's literally the cloud and the liquid ice potential temperature profile with a very sharp discontinuity at the top. This time we have observations in orange dots, a range of LES simulations in gray shading, our LES in solid, and any dash or dotted line is our parameterization or EDMF, or even the X markers at different resolutions from 5 to 75 meters. And you can see that in a way we even outperform some LES simulations in producing this cloud. Now, these clouds are very notorious for climate modeling biases. Most climate models underproduce the amount of cloud fraction here, and therefore tweak the radiation code to produce more reflectance. So it's called a too few too bright bias, which obviously might have problem extrapolating or working into future climates. After we're done with more turbulence regime, we can go to the convection. So shallow convection over land. I'm switching between variables that I'm comparing just to show you all over the map. So here I'm showing the covariances of theta liquid and total specific humidity. Again, gray is LES and colors is our EDMF in different resolutions. And shallow convection over ocean. Here I'm showing the actual fluxes that we need. If you remember the GCM equation, this is the terms we're actually looking for. And also some cloud properties as vertical velocity and liquid water. So they're literally the cloud. And overall, we're seeing reasonable match, and I've learned to adjust my expectations, what's a reasonable match when I started working on parameterizations. And last but not least is deep convection. And we're seeing very good match between profiles of theta liquid and specific humidity, good match in the timing of precipitation, even though the rain rate is off between LES and EDMF. And the last part I want to show you is the cloud top. This is a very interesting plot. So most models like us, when they model pressure drag, they either model it as a constant time velocity or some radial scale, velocity of a radial scale. And in previous work, we have tried this radial scale and did not generalize to deep convection. And what we're doing now here is we're putting this age, which is the top of the updraft, as a length scale for the pressure drag. And what we're comparing here, the gray is LES cloud top over time. And the dashed black is cloud top over time in our current model with this closure. And all the other colors are when you replace it by a fixed radial scale and just change it from one to another. So the difference is that age changes in time here, whereas the radial scales are fixed. And you can see that with a fixed scale, you can call it age, you can call it R, it doesn't really matter, right, up to the coefficient. With a fixed scale, you cannot really get the diurnal cycle of deep convection right. But once you have your scale dynamic and react to the cloud top, then you can actually capture the diurnal cycle of deep convection well. This is in progress. One of the researchers in the group, Anna, who's developing our microphysics scheme and also is very active on the EDMF group on the parameterization, has added one moment microphysics with ice, snow, and rain and everything into our EDMF. And what you see in the video is over day exactly the development we saw before. And you can see the cloud condensate, the liquid and ice developing over the day, and the cloud precipitation, the rain and snow developing over day. And so is the vertical velocity that, if you noticed before, was stretching only to barely 12 kilometers, and now it's getting all the way to 15. So our updrafts are getting higher because of phase changes, especially with ice species. And also she is examining how a probabilistic cloud scheme in the environment can affect the performance of a simulation. So you could see LES here is the solid colors, the black dashed or solid. And you could see that without a probabilistic cloud scheme, we don't get such good behavior in the cloud in terms of precipitation. And once the environment has a distribution to draw from, I didn't go into the details of how, but then you can get your properties in higher cloud better. And this is still in progress. There's a lot of errors here or issues here to deal with and such, but still like an interesting work. Maybe I would just say, if you relook at this video now, that most models produce this cycle of producing rain into a liquid into ice, rain into snow, and convection from basically from 0 to 15 kilometers with 4 different parameterizations with switch functions, or 3 or 4. And we're doing it in a single model that does it continuously. And I think that's a huge achievement. So that's, I guess, the take home. Is there any questions up to now? And how are we with time? Okay, I guess in a few more minutes. So in the last few minutes that I have, I'd like to talk about the machine learning closure part. I think some people are waiting for it. First, the data. So some members of our team, led by Joey Shen, are running LES simulations driven by existing climate simulations out there. So different AMAP simulations that are available online. She's selecting sites that are numbered here by X markers and driving an LES from large scale conditions in the GCM to get, if you like, LES not driven by observation, but by GCM in many more places. So all of these LES cases I showed you before were observation campaigns where people either measured with boats or airplanes or both, or on the ground, and constructed this setup to run an LES for a cloud scene. And this is, of course, scarce. There's 20 of them maybe, and here we can produce 200 or more, 400 simulations of different locations of the globe, from shell to convection. So of course there are problems, it's not observed and such, but these are realistic conditions nonetheless. Our models, for the most part, produce maybe realistic conditions, maybe in the wrong place or in the wrong climate, but they're realistic. And so she's selecting different things like a transaction from shallow cumulus to stratocumulus in different places, or transition to deep convection, and simulating them. And this is our data for learning. And then what we basically use is a gradient-free calibration, ensemble Kalman inversion, or in unscented Kalman inversion, which you can find in one of the papers of the group. And the idea is that you construct a loss function between the LES, the observed data, and the EDMF, given a set of parameters, and you normalize it so that everything's normalized by some covariance matrix. And this is what you try to minimize. Minimize meaning if you have some topography, you want to find the minimum. How do you find the minimum with topography? So one way is to say, I'm in this point here in the green, and I can say what's my value is what my gradient. I'll go down the gradient until I find the minimum. We call that gradient descent. It has some computational requirements, which I'll go over later. Another method is to say, well, I can't feel the gradient. I only know my value. Okay, so it will be a gradient-free approach, but I have friends. So I'm gonna call 50 friends, and each one of them is gonna go to a different spot, and we're gonna talk to each other and see who's the lowest until we find the minimum. right? So this would be a gradient-free approach. If you like, I'm almost like finite differencing the gradient, but looking at difference between different points. And so this would be the ensemble approach. And it allows us gradient-free calibration. And what I'm showing on the right, they call it epoch, but it's iteration. All these machine learning have cool names for anything, epochs. What you see here is the error here, okay, over time in the validation. I will say in a minute what a validation between our EDMF and one of these cloud simulations driven by LES that I showed on the map before. So you can see that this method converges really quickly, okay? And you can really see that one parameter, for example, this guy multiplies entrainment, starts at some prior knowledge and ends with some posterior knowledge, which is an updated value of the parameters that performs better given the matrix we chose. So this is the idea of a calibration in general. The unscented Kalman inversion, just to say on the side note, because it approximates in every set of points a distribution around them, that's what it does, you get the mean and variance. You can actually look at correlation between parameter and parameterizations. And you can produce kind of a corner plot like this that shows for a given process like entrainment, what is the level of correlation of entrainment with other processes. And here there is an assumption of a Gaussian, so I wouldn't take the value to be set in stone, but definitely the sign is interesting. What is entrainment positively or negatively correlated with, and what is detrainment positively or negatively correlated with, or any other process like the pressure closure, the mixing lengths, and any model choice. And this allows us, the ideal would be to have as less correlation as you can in this map, because it means that we're kind of overfitting, we're compensating between two closures to get the same process. So that's kind of the tool. Now, if we take an LES simulation, and I would go to what's validation here that I mentioned before, of a shallow convection somewhere on the globe on that map, and we run an LES in an AMAP simulation, we can train our model, but then we can go to the same place in a 4K warming scenario and rerun the trained model without reinforming it on the warm data. So this would be validation. So it's out of our sample. We trained in the current climate, we try to generalize the future climate. And so what we see here, let's focus only on the black line would be the LES, and then the solid green and the dash green would be the posterior, the trained of the model. So you could see that basically we generalize way well to warmer climate if we go from our current model. And that's the point here in the validation. We will come back to it after a machine learning introduction. I'm sorry, I'm a few minutes off time. I hope there'll be time for questions. So what do we want to do in machine learning? We want to take, let's say, the entrainment, and we had these non-dimensional processes, and we want to learn them from non-dimensional groups, just like people did in turbulence forever. And so we write all the non-dimensional groups that we think are related to entrainment, detrainment. And instead of saying we think this one is better than this one, we would just plug it into some neural network that would do a neural network magic and give us the right answer, right? Instead of what we did in our head, we'll do it brute force with a machine and a lot of data. The problem here is that if you really think about the architecture, we start with data from LES, we feed it along with some parameter theta into a neural network. The neural network gives us entrainment, but we don't have entrainment observed in LES well. It's not very reliable and it's hard to produce. So we have to put the entrainment in our cloud model, which is 8 partial differential equations, very complicated, nonlinear, produce a profile, compare it to LES, calculate our loss function, and now go and do what the cartoon does here really nicely, backpropagate the information to update the parameters. So this backpropagation basically requires taking the derivative of the EDMF model in parameter space. Here, theta is parameter, not potential temperature. And this is not going to happen. It's 8 partial differential equations, nonlinear with saturation adjustment processes. It's just not going to happen. And this is part of the reason that some groups, when they apply machine learning, they choose to apply it directly to what you can observe, meaning the vertical profiles, and basically throw the parameterization out of the window and just put a neural network instead of it. I suspect that's part of the motivation. What we're saying is that if you look at the components here, you can reshuffle the components in a way that could be done gradient free. So if you now think of the parameters going into your model and the data going to the EDMF model, And part of the parameters of the model are neural network parameters that are fed into a neural network. And that neural network gives you back entrainment. You can send this entrainment to the model, produce a profile, and instead of doing back propagation in derivation, partial derivatives, do the calibration you said, right? You run 50 models in different values, you look at the differences, and you try to guess the next step until you converge to the minimum. So instead of looking for the gradient, we're just going to run the model a lot of times, okay? And it ends up not being so many times, like 50 ensemble members or even 20 could be enough, depending on how many parameters you have in the neural network. And so this is our approach for applying gradient-free. It's machine learning as an inference problem. There's a recent publication online. I will show the lists in the end, and you can look at it. And just to show before this kind of AMAP and 4K validation, the current climate and next climate shallow convection. So here is an example, and let's focus again only the green lines. So the solid green line is the hybrid, the combined machine learning and physics parameterization, and the dashed green line is the physics only parameterization of entrainment. And you could see, let's look only at liquid water in the cloud here. You could see that the solid line actually fits better both the training, but also the validation, meaning it generalized here better for warmer climate, but there is an issue. And the issue, of course, is that if you look at the change of the error with time, and here we just zoom on a longer time but a shorter span, you could see that the hybrid machine learning combined with physics model has a minimum error and then it increases, whereas the empirical or physics model only decreases. What it means is that the machine learning starts to overfit, okay? And so there's the kind of a cartoon I found online that the difference between knowledge experience ups and overfitting is encapsulated in this over-imaginary, like kind of interpretation of the data. So this is still work in progress. And my personal goal of, once the CliMA AMAP is running is to start looking at interacting with parameterizations on multiple columns. So you can imagine taking a domain and putting a bunch of columns and running a hurricane or something and start to understand how closures of entrainment and such in the updraft affect the fluxes that might affect the eye wall or the warm core of a storm and such. And I think that this kind of multi-column approach that some people already started has a promising field to take the next step in having climate models address specific phenomena. Okay, I hope it wasn't too fast or busy. A quick summary, we have extended the EDMF parameterization to be time dependent, and we can show that it generalizes across multiple regimes. We can add some one moment microphysics and get ice and snow. We can add stochastic components and get more realistic, and we can add neural networks and learn from data. I will take questions if there's any, and if you want to take a screenshot of this, it's some selected publication I thought would be relevant for this talk. Thank you.
Thank you. So do we have any questions? Usually we try to start with questions from the students. So are there any student questions? I'll applaud too, but looks like there's a bunch of applause. Anyone have any questions? I'll open it up since we don't really see any student questions.
I see it.
Looks like Serena has a question.
Serena? Hi, yeah. Can you hear me?
Yes.
Yeah, I was just curious as to how EDMF deals with multiple plumes in the same grid, or?
So basically you can write the equations for multiple plumes. They're actually written like this in the papers, but it's just so bulky because everything has to have a summation sum on it that I just wrote it for one plume.
Okay.
There is, the crux of the matter is you have to decide if the plumes are entraining and detraining to each other or only to the environment. This is akin to what in physics in Heising model in physics or something, people would call it the mean field approximation, right? Are they interacting only through the mean, or are they interacting with each other? And it's really somewhat ad hoc, because this is an imaginary model in our head, and we don't know where each plume is, right? They could be all centered in the center of the domain, or they could be equally spaced. And then, of course, whether they entrain to each other or to the environment changes. That would be the convective organization of it. So we haven't dealt with it yet. We can run our model with multiple plumes. We have tested with it. We haven't found huge benefits yet. We suspect that when we start adding these stochastic entrainment closures that I showed you, then the multiple plume interaction would be very interesting and beneficial. I hope it answers your question, yeah.
Looks like Nuo has a question.
Yes. I'm still wrapping my head around the ensemble method that you talk about. Like, how does it minimize the cost function?
That was here. So basically, there's an algorithm in which, given the value, you randomly start your model with different sets of parameters, depending on how many ensemble members you want. Let's say 50. So you pick 50 random combinations of your model parameters, but you can pick them from random from a prior distribution or bounds that you say, you know, this parameter, I don't know exactly the value, I know it's positive and it can't be more than 0.1. So pick something random there. And then you have 50 evaluations of the topography that you see here in the gray shading, right?
Mm-hmm.
Broadly speaking, with 50 points here, you can kind of think where the gradient goes without knowing a gradient, right? Because you see that this point is lower and this one's higher and this is lower and this is higher. So there's an algorithm to kind of try to optimize what would be the next 50 sampling points you want to get to even further understand your field. Not to go just to the lowest one. You don't just go everybody to the lowest point, but you say, no, let's reevaluate or reorganize ourselves slightly and see where the minimum is now. And so you repeat this enough times, you very quickly, actually, as you see here, sometimes 5 iterations already get you to the minimum. So it's a very quick algorithm. A lot of time people actually add noise to it so it doesn't converge too fast, because it's converged so fast that you kind of lose track of any uncertainty. These models are very fast to converge into minimum. I hope that helps a bit.
Yeah, it helps. And that would be some method that applies to linear or nonlinear functions. So linear optimization or nonlinear optimization.
You can run it on anything. It could be nonlinear.
Okay.
For us, the model is a black box. For the ensemble Kalman method, the model is a black box in which you put parameters, you get out the value. You don't even know what's that model, right? It's a black box. You put a parameter, you get value. Now I'm going to learn how to get the minimum value by changing the parameters. That's kind of the idea.
Yeah. Thank you very much for explaining.
Yeah.
Evan.
Yeah, hi. I have a related question. And so in this graphic that you have, that's a nice visualization. You have a single minimum that they're kind of congregating on. Do you run into problems with like multiple local minima where it can't just decide where to go?
So that's the part where people add something stochastic to you see these little wiggles of them. You want to be able to let them jump out of local minima and find the global minima. It's always a difficult problem. So far, our calibration is been doing okay, but I'm actually working now on the best way to do that is once you calibrate, produce this topography map around it and see that you're actually in the global minima and not the local minima. But one of the popular techniques is called simulated annealing. It's based on the idea of how metal cools into you make a sword, let's say, or something. And so then the idea is that there's a probability of you climbing up the gradient or going out of local minima that is proportional to the temperature, the height. And so there's some kind of an added noise with a probability that decreases as you go lower and lower. And so in the process of looking for the global minima, if you're stuck in a local minima, you still have some probability of getting out of it. But it's always a challenging problem. It's not, I can't say we have a clear solution.
Yeah, I also imagine that you might get that question a lot based on that graphic. I feel like I'm probably not the first person that's asked it. And another related question. So if you do have multiple like local minima where your parameters are getting around the same amount of skill, could you like look at why one minimum works and why another one works and try to learn something about the differences between them?
Yes, if we do, this is still kind of all under progress, but this is what I mean when I want to produce these topography maps. For the topography map that you see here, it's for the visualization, but it's not produced by the ensemble Kalman inversion necessarily. You have to rerun the model on the whole range, kind of in a grid search, and get the topography. So we're working on visualizing it. And I think at that point, combined with this correlation, because basically what this map tells you is that there is some correlation with y in x here, because the slope is, if it was 1-to-1, it was complete correlation, right? Yep. So in a way, in this illustration, which is not really from the EDMF, it's just a graphic visualization of, I think it's Lorentz model that somebody in the group ran, but I just wanted to show the point. But you do have some correlation between parameters here. And so you want to explore these things, and so does local minimas and global minimas. And I think before you look at the topography, it's a bit of a blind, search. I put the parameters, I got a value, but they don't understand why. Yeah, so definitely.
Gotcha. Thank you. Great talk.
Thank you.
Thank you. Yeah, it was a really interesting talk. A lot of different things there combined. I was interested in the diurnal cycle of precipitation, and this kind of finding at the radius of clouds. You needed to include a changing radius of the clouds to get this kind of gradual deepening of convection that you see in the LES. And I was just, so that changing radius, what is that tied to in your parameterization? Like what's controlling that? Just the depth of the convection? Or
yes, so age here is literally the depths. It's basically the measures that's plotted, age. We're plotting age in a way. Updraft top is age. So basically you take the top of the updraft, the extent of the updraft from the surface to the top, and you put it as a length scale in your pressure drag, which is otherwise the same except for the scale in the below. But then you can imagine if you have very low updraft, the drag is very strong, right? Because this is small, so the drag is strong. Strong drag would inhibit the updraft from progressing. But then, what happens here with time that we don't show in the plot is the surface fluxes are increasing. This is 7:30 a.m. and this is 1:30 p.m. and this is in Brazil. So it's getting hot and hot and hot and hot. So you cook basically you cook the air. And at some point, updrafts are starting to penetrate in spite of the very strong drag. But as they penetrate, their own depth decreases the drag and they penetrate further. And so I don't have a full explanation to it, but I think it's a curious result that you see that with a fixed scale, you always get the convection starting too early. And then, here you could say maybe it's better, but you won't get the full deep convection. And here you got the deep convection, maybe right, but you wouldn't get the timing off. I think, and these papers still haven't been published. We had issues with reviewer 2 as usual. But we're hoping to publish it soon. We need to find time to refurnish it. But I think it's an important message for the community studying convection. Kind of told you that on the one-on-one conversation before. I feel like people has been blaming only entrainment when cloud models don't work. But I feel like when it comes to deep convection, the pressure is just as important. And,
yeah, that's interesting, because people think of the cloud radius as also having to do with the entrainment, right? So, but you're arguing that it's really the pressure drag term here, and
yes.
you're not relating the entrainment to the cloud radius at all.
No, the entrainment in our case, that's a good point actually. If we could have, maybe it would have worked. In our case, the entrainment, we came up with it's in literature, but we're using a length scale of B over W squared, the buoyancy and velocity ratio, which is agnostic to the radius of the cloud.
Right.
I think there's a problem probably it's not so easy to come up with a radius of cloud.
Sure.
In these, because we're simulating some coarse-grained systems. So when our updraft represents the average cloud property, it's not even a cloud per se. Our updraft is the average of all upward motions. If we have 1 or 2, it's not really a cloud. but it's much easier to look at the depth of the updraft. And you could argue that up to some aspect ratio, the two are linked anyway. So if you wanted to have a cloud radius, maybe it would be h times some kind of some aspect ratio that you can assume. And you know, these clouds do have an aspect ratio that's skewed. They're not like cubical or something. They're very elongated, so some aspect ratio.
Right, okay. So the entrainment is not tied to the cloud radius at all, but
in our model it is.
Yeah, okay. Thanks. Any other questions? I guess we're kind of out of time.
I apologize, I should have dropped a few slides.
Oh, no worries. No, you finished. We just had a lot of questions. Okay, so let's thank our speaker again. Yeah, little clap signals. And thanks everybody for coming to the talk, and have a good rest of the week.
Thank you.